something you want to say?
How did you get the color to hold?
I haven't bought cheap shampoo since 10th grade. I look at the shampoo prices and like, that's possible to buy, and I start crying. So my shampoo and conditioner cost like $30.
Oh my god.
Yeah, I know.
Alright, so for our last speaker, let's give Jack your attention so he can tell us about human heat stress, major health issues of global warming. Thank you.
Yes. So let me tell you about the work I did during the summer. It's a RU program, research experience for undergrads. So the program I did was hosted by SCRIM Summer Scholars. SCRIM stands for Sustainable Climate Risk Management. It's a program that focuses heavily on global warming issues like hurricane hazard, modeling participation, sea level rise. So it's an organization that heavily focuses on sustainability. But we don't ever think about sustainability. So that's me and Eli. Eli also did the same program as me. We live in the same house. Yes. So let me tell you about heat stress. So when we think about global warming, we think about like loss of sea ice or accelerated sea level rise. But we think, nah, that's too far from us. That's never going to affect us. However, global warming has direct effect on our human body. If temperature rises, we can experience heat wave, we can experience heat stress. So heat waves are a very critical issue in India. Reports that between 1992 and 2015, 22,000 deaths happened because of that. And now in China and southern part of the US, we experience heat waves more and more frequently. So it is a pressing issue. Let me give you a little background on human body internal temperature. So the normal internal body temperature, there's a range, it's not a fixed point, ranging from 36.3 to 37.1 Celsius degrees. And to put into Fahrenheit, it's 97 to 99. But from now on, I'm going to stick to Celsius because that's on the same scale as Kelvin. And heat exhaustion starts to kick in when your internal body temperature reaches 3 degrees above, and you start to experience dizziness, headaches, nausea, vomiting, and blurred vision. And if your internal body temperature reaches 40.6 degrees, you will have heat stroke. And within minutes to hours, you will die. So it's very scary. There are previous work done on related issues. For example, in 2010, there's a paper by Sherwin and Hooper. And the conclusion is that when a human is exposed to an environment with wet bulb temperature greater than 35 degrees for a few hours, you can experience heat exhaustion, heat stroke. So the wet bulb temperature here, you might have heard the term before, but there are 3 measures for temperature. There are dry bulb temperature, which is the temperature we normally refer to. That's when you put a thermometer outside, and that's the temperature measured. And there's also dew point temperature. That's when the relative humidity hits 100%, total saturation. That's the temperature you get. And wet bulb temperature is something in between. That takes the relative humidity into consideration. So you measure that, you put a wet sock around a thermometer, and that's the temperature measure. And that's the temperature an object can reach through evaporative process, through sweating, because that's how we lose heat. So this is temperature we're interested in. The maximum temperature, wet bulb temperature today is less than 31 degrees. So you can say, hey, it's still like 4 degrees off, so there's nothing we can worry about. But that's not true. The 35 degree here is the result of their model. And there are a lot of issues with their model. It's very idealistic. The person they have is a healthy, well-conditioned person, and at rest, indoor. So they didn't consider maybe people suffer from obesity, where it's harder for you to dissipate heat. It didn't take consideration of if you're doing some activity like playing or running, you generate more heat inside. Or sunlight or wind speed, a lot of factors can affect this model. So the goal of our research is to make a realistic model that takes a lot of things into consideration and verify if 35 is the threshold. Now this is the temperature model that we made. I promise you this is the only technical slide we have here. So bear with me. So basically this is the model. We have metabolic heat generated inside. We have radiation coming from the sun. We have evaporation going out. We have convection between air and us. We have radiation going out. So the model we have is a core shell model. We treat a person as a core and a shell. The shell is in contact with the environment. So we have we calculate the heat flux. We have the solar radiation coming in. We have the sensible heat, where the air, if the hot air comes, it brings heat into your body. If cold air comes, it takes away heat from you. We have the core flow, where you generate heat from the inside, and that heat flows to the outside. So that's the heat coming in. We're also losing heat at the same time. We have latent heat, the heat you lose from sweating. We also have the black body radiation, because everyone radiates black body radiation. That's the heat flux for the shell, and for the core, we have the heat generated inside minus the heat flow to the shell. So that's the heat flux we get. And how do we go from there to the temperature change? We all know the equation Q equals Cm delta T. So we can divide Cm to get the delta T. So Q is the heat flux. This is the specific heat of a human body and mass. And you see here, we have alpha here. Alpha refers to the ratio of the shell to the whole mass. So that's this term here is the mass of the shell. This term here is the mass of the core. So we do that, we calculate the delta T, and we add that to the T we have right now. So we made a fixed point iterations to calculate what's the next heat, what's the next temperature, until we reach the steady state when the heat flux equals 0. So this is the C++ implementation. I'm not going to show you the model, this is just a snapshot, but 90% of work goes in here. So there are tons of equations. So, oh yeah, how is this more realistic than the model they're using? Because a lot of these terms depend on those factors. For example, metabolic heat depends on the activity you do. Let's see, like core flow depend on whether you suffer from obesity. It affects blood flow. So a lot of equations go into these terms. And this is the result we get. So let me explain one of them, then the rest of it is clear. On the x-axis is wet bulb temperature of the environment. It goes from 20 to 40. On the y-axis is the internal body temperature. So for here, let's look at the blue curve first. It's a person in shade. So as the wet bulb temperature rises, you see within this range, our human body can still adjust to the environment. So we can still remain, the internal body temperature can still remain in the normal range. But once it passes this point, we start to lose control. And it hits the heat stroke here. That's about 38 degrees. So if you look at the partial sunlight, it corresponds to about 35. So that's the number we get from the Sherman-Hoover paper. But if we are under direct sunlight, we see this temperature goes down to 30 degrees. So we see it drops really fast. But that is just one variable. We use separation of variables here, and you see the activity you do also affect the critical temperature. For resting, it's here, for walking, for jogging, for tennis. And this is wind speed. So if we have 1 meter per second wind speed, we can adjust it well. But if the wind speed goes lower and lower, we see the temperature also goes down to 32. This is people suffer from obesity, like if you're healthy, it's there, obese and highly obese. So a lot of things can affect that critical temperature. And this is just one of them. If you combine them, it gets much scarier. So please start acting now. It's a really critical issue, and it has direct consequence on us. So what did I take away from the RU? What did I get from the RU? First of all, I got a motorcycle. The point is, the program offers very generous stipend, around 4.5, 5K. That's the most money I got up until this point. You can have the experience to be guided by a research mentor. You will be exposed to scientific research. I do work with a lot of graduate students on different topics, but we work in the same office. So basically the same thing. You do research, you find a topic you're interested, and you just work on it. You can meet new friends who are interested in similar problems, and it's possible you can get some publication out of the research. For example, last year I did research with Professor Lars English, and we have a publication. And this one, the work is still in progress, and we expect to have something published. And it can also help you with your graduate school application, because for applying for RU is very competitive. For this program, we have more than 300 applicants, only, I guess, 20 of them are applied. So if a school sees that, it means that you're very competitive. And overall, it's just a great experience. So I recommend everyone, if you're interested, you can give it a shot. And just start search now and start applying.
Did you take into account any differences in, say, body structure, for instance, like a tall person?
So this model is still, realistic as it is, it's still primitive. There is a lot of things can be refined, so I didn't take that.
If you go to that slide, we show a bunch of curves, a bunch of data. One thing that struck me, what kind of surprised me is the one on the top right.
Yes.
Like if you're playing tennis, is that like in direct sunlight? Because that seems like a low
Yes.
wet ball temperature.
Yes, this is just to showing you the different effects. Because human body is very complex, it's dynamic.
Right.
We can adjust to very, how do I say, like, crucial experiments. But for this one, this experiment is very static. Mm-hmm. It is just, nothing is changing during the experiment.
Right.
So that is very low indeed. But
that's like in Fahrenheit, that's like what, 6?
Right, that's very low. That's
Yeah,
very low.
yeah.
Yes.
So
So
I know I can play tennis in 65-degree weather and be okay.
yes, I agree with that. But
Yeah.
yeah, this is just showing you how activity can affect your body.
Right.
So this is to some degree accurate, but to some degree still away from reality.
Mm-hmm.
So this one still can be changed.
Is it that you're maybe not accounting for like increased sweating or something
Maybe,
like that?
maybe. Yeah, sweating. Sweating is one part that I didn't delve into much.
Mhm.
So I think for every one of these, the sweating rate is the same.
Ah, okay. That makes sense. Yeah.
And for example, there are a lot of things to take consideration. So if you imagine soldiers standing still under direct sunlight,
Right.
they can't stand for like 10 minutes.
Right.
But as long as they start walking,
Mm-hmm.
you might think when you start walking, you generate more heat from inside.
Right.
But the reality is there's more wind coming in, you feel much more comfortable. So for this model, you can't take that into account.
Mm-hmm.
But this is just a I don't know, primitive model, I would say.
Nice.
Yes.
Does this assume that you do the same activity indefinitely? Or...
Yeah, definitely. Until you reach a steady state temperature.
All right.
This concludes our colloquium. Thank you for coming.
Print my homework.
Elon, why did you do
Of course, I could go go back, I can find the acceleration of what it is. And then I ought to be able to plug that in.
That's what we've seen.
Oh, are you going to a colloquium? I was like, yeah, on Thursday. He's like,
Next time.
Cam, you're in my way. Cam was in my way. Julia.
I'm waiting up.
I'm gonna bring it upstairs.
Especially since that's also what I did myself in high school. So I already have some back. Like, dude, you gotta rock up. Like, yeah. I didn't. Stop talking. Start trying to catch up. Good job, all right. Thank you, Tomeisters, for doing the cleaning.
Well, this will be you next year. Oh, you might start practicing.
I'm a great presenter.
That was so funny. I asked Katerina, she said, yeah. I was just trying to get
Oh, sure.
Yo, why didn't you get this? Yo, it was so funny when you put that everywhere. I was like, that kid next to Jackie looks just like Eli. Like, what?
Sorry, the Nick Vasco.
I'm okay, thank you.
Basically, they're like breaking sparks, like screaming where they're becoming something different. But he said it's like basically the same people doing the same stuff, but they're not called scream anymore. So he said like they have all this extra money that they're trying to get rid of. Because
It's a name.
Because if they, under their name, because they can't keep it. So I think he was saying that like that's part of it.
Exact same situation. They had like this huge massive program where they would bring like all of the students from like all of the different ones. Like, it's called NNIIN, so it was like all of the different, it's like, I think it was like 18 different schools, and they'd have them all go to the same place, and everybody would give their entire, like, talks in an entire week, and you did nothing there, and you were just there for a week, like, listening to talks, with like hundreds of students just there, which was kind of nice, because it's like, you don't do anything for that entire week, and you're just there, and you just go and like talk and hang out with people that you already know.
Yeah, we have a sports club council.
But then they can't do that anymore because they ran out of the funding for the grant that they had, so they had to get it again.
Hey, Jackie.
Literally like this year.
Tyler, catch.
Because they would also publish all the timings in a single week. 1:30? Like that.
I believe that.
Yeah, like every student's article, and you're talking about
I was gonna go back to my room and celebrate. That was such a good presentation. Not today.
Yeah, you
Not
give
today.
100 students 5K.
Because I presented. I
That
did well.
quickly becomes 100,000.
Yeah, and that's like